All right, guys, so pre-calculus, some more trig identities here. We're going to get into what are called sum and difference formulas, and these allow us to do some new things. We can, for example, find exact values of trig functions for angles that may not be on the unit circle. And what we can do is we can use two angles that are on the unit circle and maybe combine by adding or subtracting those two to get a new angle. So let's take a look. You see these formulas here for sine of u plus v and sine of u minus v. And basically, if you look at the pattern, it's basically the sine of the first angle times the cosine of the second angle. And then for the formula that's plus, there's a plus, and then it's cosine of the first angle and sine of the second angle. And then you notice the only difference for the minus is that you have the minus in there. So sometimes you'll see this formula written as one single formula. For example, the main one, the original one as written again, is just sine of the first angle times cosine of the second angle, and then it's plus, and then the trig functions just switch. And what you can do is, if this formula ends up having a minus in there, you can just put the minus down there, and this kind of just condenses these two formulas into one statement. Okay, and we're going to use these in a sec. I'm just kind of introducing. And now there's another set for cosine. If you have the cosine of the sum, you can see that it's cosine of the first, cosine of the second, but then it is a minus, sine of the first, sine of the second. So the condensed version for cosine of a sum, again, is cosine of the first, cosine of the second, but it's now the opposite sign, and then it's sine of the first, sine of the second. And if you end up doing the cosine of a difference, you end up using the plus over there in the formula. Okay, and again, we're going to do some examples very soon. Okay, and then for tangent, you see tangent of something plus something. The numerator is kind of just like distributing, which you really can't, distribute trig functions, but that's what the numerator looks like. It's tangent of u plus tangent of v. And then the denominator is always 1 and then the opposite sign. So if this is a plus, it'll be a minus here. Tangent of u times tangent of v. So the rule to condense both of those into a single rule, again, the numerator is just basically kind of like you're distributing tangent of u plus tangent of v over 1 minus those two multiplied together. Okay, and if you are doing a difference, then you'll have a minus here like you distributed it, and then this one will actually always be the opposite. Okay, so those are just the formulas. Have those written down, have those available where you can refer to them, and let's get into seeing what they can really do for us. Okay, one thing we can do is something like this. We can find the exact value of the tangent of 75 degrees. Okay, so again, the new thing here, 75 degrees is not a unit circle value. Okay, so we don't know the exact value of it, but it can be thought of tangent of 75 degrees. If you can think of a way to get the 75 degrees where it's something plus something or something minus something, where both of the angles that we use are unit circle values, then we can make this work. So 75 degrees, one way to do that is just 30 plus 45. Okay, and I chose those because those are both unit circle values. You want to pick a 30, a 45, or 60, and that could be in different quadrants. Remember all the different reference angles. So really what's going to happen here, this is going to be like the u plus v part, okay? Or some books just use a plus b in their formulas. I may mention it that way. But what the formula says is that it's, remember, distribute. It feels like distributing in the numerator, so it's the tangent of the 30 plus the tangent of the 45 over 1 minus the tangent of the 30 times the tangent of the 45. Okay, and what we can do now is, since 30 and 45 are unit circle values, we can go ahead and simplify this a bit. Okay, so let's just think about the tangent of 30 we need. So the tangent of 30, that's the root 3 over 3. Okay, remember the three main ones. The 30 is root 3 over 3. The tangent of 45 is 1, and the tangent of 60 is just the root 3. Okay, if you just remember those, and then you can use the different quadrants where they may be negative, Those are like the three big unit circle values for tangent. So the tangent of 30 is, again, root 3 over 3, plus the tangent of 45 is 1, and then we are over 1 minus tangent of 30 again, root 3 over 3, times tangent of 45, which is 1. Okay, so where this can get a little messy, especially with these tangent ones, is when we have to do some simplifying. Okay, so we have all these fractions within fractions and whatnot, so why don't we simplify a little bit? First off, we have root 3 over 3 plus 1. In the denominator, we have 1 minus, if we just multiply that root 3 over 3 times 1, it's just root 3 over 3. So what we want to do, we don't want to leave these fractions within fractions. So what I want to do is actually multiply top and bottom by the 3, which is in the denominator right here. And what that'll do is they'll get rid of the fractions that we have in the numerator and the denominator. So when we multiply by 3, we'll get, it'll be 3 times root 3 divided by 3, so it'll just be root 3 plus 3 up top. And in the bottom, we'll have 3 minus root 3. Okay, and now again, we don't want to leave an irrational term in the denominator, an irrational number, so we're going to have to rationalize that as well. So let's do that. And we rationalize by multiplying top and bottom by the conjugate, okay, like we did a while back. Okay, and this is one of the messier problems. They're not all going to take this long with the simplifying, but this one just happens to kind of show a lot in the simplifying step. So if we just kind of multiply that out, so numerator, we're going to get 3 root 3. Root 3 times root 3 is just 3. 3 times 3 is 9. Plus 3 more root 3's. And it's our denominator that should really simplify down quite a bit and become a real number with no, or I'm sorry, a rational number. So when we multiply there, we're going to get our 9. Then we're going to get our plus 3 root 3. And here's why the conjugate's going to help, because when we multiply here, we're going to actually get that opposite term to cancel it out. And then when we do the last, we'll get it minus 3. So we are now at, what do we have? In the numerator, it looks like we have 3 plus 9, we have 12 plus 6 root 3's. And in the denominator, we have 6. So we should be able to reduce that down a little bit farther now. Let's move this up out of the way, a little smaller. Okay, the 12 over 6 part will reduce down to just 2, and the 6 root 3 over 6 will just become root 3. Okay, so that one ended up, again, it had a lot of steps in here that only really seem to happen with the tangent problems, because a lot of times you're going to get these, you're going to get, like we got here, these fractions in the fractions, and you do have to simplify them down. So that's just kind of the way that one goes, but that's an exact value. The 2 plus root 3 is an exact value for the tangent of 75. All right, let's take a look at another example. Here we need to find the exact value of the sine of pi over 12. So pi over 12 is an angle in radians. So we would need to find some sort of way, using pi over 6, pi over 3s, pi over 4s, to maybe get the sum or difference to be pi over 12, and it's doable. What you might want to do, though, for this one is just kind of get it in degrees. The final answer is just going to be a number, and it doesn't really matter what unit the angle is in for this one, right? Because we're just finding the sine of some angle. So if you want to, let's just convert the sine of pi over 12. If we want to go into degrees, is really, remember, the pi is equal to 180 degrees. And 180 divided by 12 is just going to be 15. So this problem really kind of boils down to, what is the sine of 15 degrees? Okay, so for 15 degrees, again, we need to find angles that we know, angles that are on the unit circle, that add or subtract to 15. So I'm just going to go ahead and use 45 minus 30. Okay, again, 45 minus 30 is 15. That's going to be like our u and our v, okay, or the a and the b. And the formula for the sine, for the difference of sine, is again sine of the first, cosine of the second. Move this over a little bit. Then it will be the same sign that we have here. So minus, but then we switch the trig functions. It's now cosine of the first angle and sine of the second angle. Okay, so if you go back and look at the formula, again, we'll just show it since this was the first time. The sine of u minus v, remember, is sine of u cosine v minus cosine u sine v. Okay, so that's kind of our setup there. And now we just got to go and fill these values in, okay? And these should be unit circle values that we know. I try to use 45 whenever I can because I know those are the root 2 over 2's. So the sine of 45 is root 2 over 2. The cosine of the 30, if we think about 30, 45, 60, I know that the 30-degree angle has the small y value, so the cosine of the 30 is the root 3 over 2. Okay, the cosine of 45 again, they're both root 2 over 2 for 45. And then the sine of 30 is the 1/2. And we just kind of need to simplify this. It's just multiplying fractions. It's not going to be nearly as messy as the tangent problem. We're going to get root 6 over 4 minus root 2 over 4. And since they already have that common denominator, we can combine them into one single fraction. And we will end up with root 6 minus root 2 over 4. And a lot of these problems with sines and cosines, you're going to get some similar numbers, either root 6 plus root 2, root 2 minus root 6 over 4. A lot of these you'll see kind of show up the same way because when you're multiplying like these numbers on the unit circle are the ones that show up all the time. Okay, so that's the exact value for the sine of 15. Okay, we didn't have to just throw it in the calculator and get some decimal. By using this rule, we were able to get an exact value. All right, some other things we could be asked to do is to take a like an expanded expression, like the example A here, like this guy, and can we turn it into a single trig function? Okay, so we kind of have to look at the format of it. It's the sine of 110 cosine 65 plus cosine of 110 sine 65. So I copy and pasted the formulas again back here just so we could remember the one that has sine of an angle and then cosine of an angle plus cosine of an angle sine of an angle. That's what we have here. That's the setup for the sine of the sum of the angles. So this expression really is just going to be the sine of the 110 plus 65, okay, which of course should be written as a sine of 175. Okay, so this is the single angle expression that would equal that. Now that one we wouldn't be able to get an exact value for because the angles are not unit circle values, but we could still write it as a single trig function. Okay, part B, a little bit easier. It's clearly a tangent. It's clearly the sum of a tangent because it's that numerator again where it's kind of like distributing. And then just make sure the denominator fits the pattern. It's 1 minus the two things multiplied together. So this one is really just going to be the tangent of the sum, 45 plus 60, which is 105 degrees. Okay? And that one we could get an exact value for, kind of like the very first example we did. It got real messy when we had to simplify those fractions. But directions here, we're just kind of write it as a single expression. All right, we can also prove identities using the sum and difference formulas. So let's take a look. We want to prove that cosine of pi over 2 minus x equals sine of x. So let's think of this side again as the cosine of u minus v, right? That's what it is. It's the cosine of the difference. And then we'll kind of work on that left side and see if we can get it to equal the right side. So the formula for the cosine of u minus v, again, is going to be cosine u cosine v. Okay, so it's cosine of both. Then the thing with cosine is it's going to be the opposite, so plus sine of the first times sine of the second. Okay, again, that formula was cosine u cosine v minus sine u times sine v. Okay, so have those formulas out until we get them completely memorized. Okay, and now we want to go through and just start simplifying, okay? The cosine of pi over 2, if you think about pi over 2 is up here. The cosine up there, what's the coordinates there, right? The coordinates there are 0, 1. So the cosine of pi over 2 is actually 0 times the cosine of x plus, now the sine of pi over 2 is 1 times the sine of x. So 0 times cosine x is just 0, so we're just left with 1 times sine of x. Okay, so sine of x equals sine of x. We proved it. Okay, both sides are sine of x. You just needed to go through and substitute some of the values in and evaluate the ones that you know, and then just using algebra, things kind of clicked and worked for us.